Okay, sounds good. So let's recall sort of what a magic state distillation, which I will abbreviate as MSD, what this sort of protocol does. And so I grabbed this from this, at least this sort of distillation of the protocols by Campbell and Brown. Maybe, sorry, no, that's not possible. Something like this. Okay, so the basic idea is you start with taking n copies of a resource state. Could be a single qubit resource state, but it could be multi-qubit. Let's just call this rho. So in many of the protocols, there's this second step, which they call twirling a Clifford. So recall that in these magic state distillation protocols, what you're allowed to do is that you have ideal Clifford operations. So you can do Pauli measurements and Clifford unitaries, and you can prepare stabilizer states ideally. But you are also allowed to have a faulty resource state. Twirling a Clifford is basically probabilistically applying a Clifford or not, or its inverse. So you probabilistically, so if you have some G, you can apply I, G, G dagger, where G is an element of the Clifford. Usually we're thinking of Clifford 1. You probabilistically apply one of these, and what it does essentially is it prepares the state along a particular axis. So I will give an example later when it's the Hadamard. And then so you define a N1 stabilizer code. Essentially, you're embedding one logical qubit into n physical qubits. So you have to define an appropriate stabilizer group, so on and so forth, and we'll work with a concrete example. The idea is that you want to have n physical qubits, and then you want to have a logical subspace of dimension 2. And I will see if I can just try and fit this in here, where you finally, so you define the stabilizer code, you perform measurement onto this eigenspace. So I will skip that. It's sort of implied in this third step. And then in the fourth, when you post-select on the measurement being all +1 eigenvalues for these stabilizer generators, you decode, which means that you want to map the logical subspace onto one of the physical qubits, which is the output of your distillation. And you can always decode this using a Clifford unitary. Okay. So let's start with this question that we had talked about last time, and we will discuss a magic state distillation for this so-called H state, which I will remind you guys what that is. So universal quantum computation, is there a tight boundary for pure states? Okay, what do I mean by this? Okay, so let's let's recall that we have this picture. This is the block sphere, or at least a profile of it. And so let's take the 0 state to be up here, the plus state to be up here. And this is the totally mixed state. So last time we distilled the T state, which is hard to picture here. But what the T state is if you imagine the stabilizer octahedron, it points directly through the center of one of the faces. And what we found is when you use this 5-qubit code that Bravi and Kitaev sort of used, or this 5-qubit distillation, you find that the T state, if this is sort of the boundary, I'm just going to draw this, and you have that this is the T direction, then this is the stabilizer, and you can distill. If you have an error between the state that you start with and the stabilizer, no, the error is between this pure state here, which is going to be T, and this is the stabilizer polytope, or at least the facet of it, then the distillation works well if you have an error that starts, say, here, but it doesn't come all the way to the edge of the stabilizer polytope. So here we are going to distill the H state in what Reichardt shows. So here we have this H state, and this is the +1 eigenvalue, so I can call this H0 perhaps, and then H1. So what Reichardt shows is that if you distill any state, and there will be a parameter that varies from epsilon equals, this is epsilon equals 1 to epsilon equals to 0 when you get here. There's no error if you're actually distilling this state, and there's 100% error if all you get is this state. He shows that more or less that this boundary that Okay, sorry, can you guys hear me?
Yes.
Okay, thank you. Sorry about that. Okay, so hopefully this one works. Just give me a moment. I will charge this other one while I... let's see, that's right. I wanted to get another color. Okay. So okay, so consider that we had a state that was right here. Suppose that there's some that we consider a convex mixture of these two stabilizer states an even mixture right here, which I will call rho star. So the reason I'm picking this state is I want to figure out what its fidelity is relative to H0, because that will define this boundary here. So since it's an even mixture, you have that rho star is equal to 1/2 0 0 plus 1/2 plus plus, which when I write these in terms of Pauli's, this will end up being 1/2 I plus x over 2 plus z over 2. So now recall we also have that this H state, if I forget to, H is just H0, the +1 eigenvalue of the Hadamard operator. So this state can be written as 1 I plus 1 over the square root of 2 x plus z. And we want to compute the fidelity fh of rho star, which is equal to h rho star h square root . So when you just let me compute what's under the square root, I will not do out the full calculation, but it's just you do this inner product and then you use some trig identities. It's not too bad. So sorry, okay, star. And this, when you work it out, it's equal to 1/2 1 plus 1/2 see, cosine pi over 4 plus sine pi over 4, which these are precisely the same thing. So the whole, so this is 1 over the square root of 2, and there's 2 copies of them, so that gets rid of one of these. So when I compute the fidelity, I get fh of rho star is equal to 1/2 1 plus 1 over 2 square root, which is on the order of 0.888. Okay, so this will be an important number because we want to check later that our distillation algorithm works if and only if we get an output error that gives us something like this, greater than this. Also, just a fact that we will want to use later that's related to this stabilizer octahedron is the following. So if we have that a point in the Bloch sphere can be written as x, y, z, then the 8 facets of the stabilizer polytope which I will write maybe as SP1 for 1 qubit. They all have the form roughly of x plus y plus z absolute values, the sum of the absolute values of the coordinates less than or equal to 1. Which it's not hard to see that if you just draw one octant of what's going on, this is one of the facets. Say that this is all the coordinates are positive. you have that the vertices are polys, which are here 0, 0, 1, 1, 0, 0, 0, 1, 0. So you can see, because this is all convex, that you will not be able to have any coordinates whose absolute values are greater than the sum of them will not be greater than 1. Okay, so I won't prove it. Yes, we can do it like that. Mm-hmm. Yeah. Okay, very good. So we have this theorem, which we will prove. Theorem, so this is Reichardt. Which is that we have universal quantum computing. So universal quantum computing whenever we have that the fidelity of our input state rho is greater than 0.888. Or, sorry, maybe, yeah, I will just call this FH star. So whenever our input resource, single qubit input resource, has greater fidelity than this, which basically means that in the picture that I just erased, so long as we have a fidelity whose parameter is going to allow a fidelity that's greater than the one that we get here, we will be able to have universal quantum computation. So what is the proof uses? The 7-qubit steam code. So we won't need a background on quantum error correction. I think maybe it helps, but all that we really need to know is that there's a certain set of generators for the steam code, a set of stabilizers, and a particular sort of logical subspace, and that will be all we need to make this one work. So what's sort of the idea? Okay, I sort of sketched at least the idea. So let's go. Okay, so for a single qubit, so if we just start with some single qubit, sorry, this is not what I want to say. Okay, yes. We can write the density matrix as something like rho 0, 0, rho 0, 1, rho 1, 0, 1 minus rho 0, 0. Subject to the eigenvalues being greater than or equal to 0. And eventually, what we want is to consider a Hilbert space on n qubits where Hilbert space on n qubits, and then we will have an input state rho, which is a tensor product of this single qubit rho to the n. For this one, we will use n equals 7 for this Steen code. Before I go into exactly the precise details of this piece, let's just go through this twirling operation. And because I mentioned it before, but it helps too. So, and we want to distill, okay, also I should mention this a little bit more clearly. Objective is to distill the H state from n copies of rho. Okay, so what we're going to do is the following. So what is this twirling operation? I mentioned that it's basically a process in which you say that you have some eta of rho, which is equal to, so in the case of the Hadamard, we want to distill, so since we want to distill the H state, we're going to consider so for any G here, G is an element of the Clifford 1 group, you would have, actually, a twirling would look something like this. Identity, just rho plus G rho G dagger plus G dagger rho G. And what you can show is that the output of this will be a state that looks something. So in the case of the Hadamard, its inverse is the same thing as H, right? So in that case, we have the twirling operation looks like rho plus H rho H. So what is this doing? It's actually just getting rid of all of the asymmetric components. So the y component is going to go to 0 because what you're actually doing is you have this vector here. This is the eigenstate h. And what h is doing is essentially just rotating around this axis. So when you do this process, the only states that will be left over are ones where x and z are symmetric, and it's going to be set y equal to 0. Yeah, so this is in general, but in this case, this is the twirling that gives you this. No. I didn't do that. In general, this is what you should do. But because H is sort of special in this regard, you do an even mixture. Because in general, you can apply nothing, you can apply the unitary, or you can apply its inverse. Yeah. So this, if you do this for the T state, it will give you only density matrices that are on a line between. So what does this do? Sorry, I keep drawing this picture. What the twirling does is, if this is the H state, it gives you a density matrix on a convex line right through here. Oh, for H, it's fine. Okay. Yeah. Okay, yes. So in this case, you can show that if I use this, I can put my density matrix in a form like this. So rho can be put after this process, rho can be, and I will just abuse notation and call this state that I started with rho. After this, I will still call it rho, just know that I performed the twirling. What it essentially does is that I have this parameter x over 2. Sorry, hold on. It's 1 plus x over 2. 1 plus x over 2, x over 2, x over 2, 1 minus x over 2. Okay, so it's just a single parameter, which makes our lives much easier. Okay, so there's something that I should mention at this point, which is what is the interpretation of this x? So we can also write rho as being equal to, after this twirling operation, we can also write this as 1 minus epsilon h0 plus epsilon h1. This here is the probability of an error because we don't want h1, we want h0. So this is some initial probability of error. And so since I actually know what these states h01 is equal to 1 over 2 I plus or minus, plus if it's 0, minus if it's 1, or I could write, okay, yes, that's fine, 1 over the square root of 2 x plus z. Okay, so this is what h0 or 1 look like in terms of the polys. And so if I rewrite this whole thing, this x parameter in terms of epsilon is going to look like, just making sure I have the, where did I put that? Is it not here? Sorry, I believe epsilon x is equal to 1 minus 2 epsilon over square root of 2. Sorry, I'm just going to leave that as a question mark. Let me just check, because I guess I wrote that somewhere else. Okay, yes, this is correct. Yeah, so this is the initial error probability. This is the probability of making an error when you're starting your distillation. And what we essentially want is to, after we perform this magic state distillation, we want roughly, we're going to get a new single qubit state, and we want the out error, which will be a function, we want the out error to be something like, it will depend, okay, so maybe I should just say this. It will depend on this initial error like this. And hopefully it will decay for small epsilon. If we start with some initial small epsilon, this E out will be much smaller than the initial one. So that's basically what we want.
Actually, the first operation puts the row on the line, right?
Yes, exactly. Puts row on the line. And then, so now what we will do is we will prepare 7 copies of this. We will project to, so this is what I'm going to explain right now. So this is just this is the Steam code. So what we have here is a stabilizer which is generated by 6 elements, right? So we are in a Hilbert space of dimension 2 to the 7, and we want to have a logical subspace of dimension 2 for a single logical qubit. So we will have 6 generators. So let's call these sigma 1 to sigma 6. So these have a special structure. So I'm using the notation again where x is being applied to the fourth qubit, and if there's nothing denoted for a particular qubit, it means the identity is being applied. So x5, x6, x7, sigma 2 equals x2, x3, x6. So this is more for completeness. Sigma 3 equals x1, x3, x5, x7. And then, so for sigma, let's see, 4, sigma 5, and sigma 6, because these are what are known as Calderbank Shorb. Hold on. Calderbank, I'm forgetting, blanking. It's a CSS code. So I'm just going to replace this precise generator with Z. So, sorry, I would just swap X's and Z's. The same exact thing, I'm just being lazy. Okay. Of course, you can check that it's easier if I wrote it down explicitly. You can see that these clearly will be commuting, and even with the z's, there will always be an even number of anti-commuting pairs. So you always have that these commute. So this is okay. Okay, so how do we go forward from here? We have a logical poly Z, which just means that this operator acting on the subspace generated by these will act like a Z, like a poly Z on a single qubit. So and we have that ZL XL equals I YL. So you have that these logical polys satisfy all the right algebraic relationships for single qubit polys. So we will also define the following projector onto the eigenspace, the all positive eigenspace for these generators. So we have that I equals 1, 2, 6 of 1/2 I. This identity is identity on all of the qubits. And sigma I. Okay. Okay, and we will call the subspace, the logical subspace, we'll just define it like this. And I called this HN maybe before. So this is the logical subspace. So what do we want from here? Yeah, and n is 7. So maybe I will just call that 7. So we also want to define a basis on this logical subspace. So to do this, we will introduce this. We want a essentially some basis such that when I act my logical Z, it acts as a zero computational basis for a single qubit, and so on and so forth. So we also want ZL 1L to be equal to minus something like this. So you can show that there's, I can write 0L in the following way. I will do this out explicitly, but it's well known. So 0 bar is 0 for all 7 qubits plus 10 bar. This is 1010 repeating until you get to 7, so it just terminates at the 7th. And I will use a similar notation, 0110, also repeating. So 0110 and then 011. And then let's see, what is this one? 1100. What are these? So I'm not done yet, but these are it's 1010. You keep doing it until you get. Yeah, no, it's not going to terminate on an even. So it's 101010 and then 1. Yeah, it can cut off. You just keep going until you get to the 7th mark, and then, or else it was just going to be too much to write down. This is 3 zeros and 4 ones. And then these I couldn't really shorten to them to anything. So 1011, 010 plus 0 1 2 3 4 0 0 plus 1 1 0 1. And the 1 is going to be just given by XL 0L. And you can show that these are orthogonal. These are coming from, what are these coming from? These are even weight. So what we want is a condition like this, but moreover, we need it to also be stabilized. Each of these terms should be stabilized by these generators. So you can show that all of these are the even weight code words is what they use, is the language that they use, even weight code words of this Steen code. You can't have ones with 2 ones, because actually these generators will not stabilize those. So these are the even weight ones with weight 4, weight in Hamming weight 4. Yeah. Okay. Yes. Very good. Okay. Very good. So we have this row in. So what do we want to get out of this? What we want to do is the following. So we start with this row in, which is row to the 7th. And then what we want to do is we want to project to this logical subspace. So we want two things. Row S is going to be defined as P row in P over trace P row in. This is just the state after the projection, and we post-select on the all 0 eigenvalues, or sorry, all 1. And then also, sorry, we want the probability that you even get this state in the first place. The probability of success is just this denominator here. So the procedure is that you start with this, you project down to this eigenspace, and you post-select on the all 0, or I keep saying all 0, all 1, positive 1 eigenspace. If you get any outcome that's not +1, then you discard and you start again. So that's just what we're doing here. Also, by the way, this will be useful. We have that this projector onto L is equal to 0L plus 1L. Do I need this? Okay, I think that we're okay. So in particular, what we want is to compute this rho S. So if we were to compute it, it would look something like this normalization factor, which is just 1 over PS times 0L rho in 0L, 0L rho in 1L, 1L rho in 0L, 1L. We are projecting down to a two-dimensional subspace, and this will be the reduced state in that subspace after we do the projection. Okay, and so here I will do some cheating after some, I must say, tedious algebra. What you have is that you went from an initial state for one resource that looked like 1 plus x over 2, x over 2, x over 2, 1 minus x over 2. What is the tedious algebra? It's computing this. It's essentially taking the input that we wrote down before, the tensor product, and applying these using these two relationships to actually compute what these are, just direct calculation. Yeah, nothing special. You can use some of the facts that you have these zeros have a particular structure, and that can help you simplify, but it's not very illuminating, so I will just skip this part. But you start from a row that looks something like this, and then the final output of this row S is something that has the same form. This is all x out over 2, 1 minus x out over 2. So you have something that's the same form. So this is also still lying along the line between h0 and h1, right? Because it still has the same form. So it's still on the line between h0 and h1. And now, but we know we can compute that this x out is equal to x cubed 7 plus 8x to the 4th over 1 plus 14x to the 4th. This is this x out. And then the p probability of success is this denominator. 1 plus 14 x cubed, x to the 4th, sorry. Oh yeah, okay, that's what I was going to say. This doesn't make sense. Over 64. Good. Okay. Again, sorry, just recall. So then epsilon out is 1, sorry, it's the other way around. X out equals 1 minus 2 epsilon. So we're defining epsilon out like this. We're defining epsilon out just like this. So then we can rewrite everything in terms of epsilon outs if we so chose. Let's see, will I need this? So yes, actually, I will go over here so that I can sort of just comment on some of the results. So first thing, if you have that epsilon, the initial error probability is very small, right? This is a function of x, which is a function of epsilon. So I did not actually rewrite everything in terms of epsilon, but if you do, you find that epsilon out, when epsilon is small, goes like 7/9 epsilon, which is not great because what it kind of means is that each time you do a round of this distillation, you're only getting so each time you get a factor epsilon improvement compared to the Bravi. So this is the Steen code, whereas the Bravi-Kitaev algorithm, distillation algorithm, gives 35 epsilon cubed. So this is Bravi-Kitaev. So after a single round, the improvement is already quite drastic if epsilon is small. And then if you iterate this, you basically take the output state here and make it the input state, and you do this again, then this is going exponentially, and this is polynomially. Okay, so more. Let's talk, what is this threshold? Because, so we want, there's no improvement, right? No improvement if epsilon out equals epsilon, right? Because if epsilon out equals epsilon, you just keep the same error the entire time with every iteration. So what you can do is say, okay, well, this gives me an equation that I can solve because this is a polynomial in epsilon and this is equal to epsilon. Does that make sense? Because this is a polynomial in x, it's the same as a polynomial in epsilon. Oh yes, okay, because it's divided. Yes, sorry. No. That's. I'm not thinking of the bottom. Yes, rational function. So what's this graph look like? In terms of epsilon. Okay. Well, this is our linear. This is epsilon equals epsilon out. And when you plot this, you find that there's this when epsilon equals to 1/2. Sorry, let's make sure. Yeah, when this equals 1/2, we have, this is precisely the value, no, that can't be, sorry. Is this epsilon equals to 1/2? It's there, okay, I will call this epsilon 0 because all of a sudden 1/2 doesn't really make sense. But the Steen code basically has a curve that looks like this, where it intersects precisely once, one non-trivial solution, precisely at this threshold, and this is precisely corresponding to FH star. It's not equal to FH star, but this value of E0 is precisely what corresponds to FH star, because we have this relationship, epsilon is equal to 1 minus FH squared. So this value, so epsilon 0 is equal to 1 minus FH star squared. And then we have this, okay, so this is actually red. So this is Bravi and Kitaev. So this is, it's like it's exponential, so it's a little bit more steep, but the threshold is, there's a gap. Okay. Okay, so a couple of other things to mention here, and then I will get to something else. So there's a couple of corollaries. One is that, so this proves it, by the way. So there's one corollary. So if I take operations that are stabilizing, stabilizer operations, and I include with them a resource state psi, where psi is an element of C2 minus the stabilizers on a single qubit. Okay, hopefully that notation is clear enough. So basically, if I just include with stabilizer operations any single qubit pure state that's not a stabilizer, then I have universal. Then this gives me universal quantum computation. That's one. And then there's a similar sort of result if I take stabilizer operations and let's see. So this could be an n qubit resource state, not a single qubit resource state, such that phi is an element of C2 to the n minus stabilizers. Then this also simulates universal quantum computation. And then, so the question that you're left with is that, does this hold for multi-qubit mixed states?
Does the first one follow immediately for what you just showed?
To me, it doesn't. No, to be honest, when I saw this, he gives a proof of this, and the proof relies on the single qubit case. But to me, this is not immediate.
Right.
But I saw in other places in the literature that people are saying that it's known that for if you just include any pure single qubit stabilizer, or sorry, single qubit state that's not a stabilizer, then it follows. But to me, it's not clear how.
So he gives a proof of this separately.
Of corollary 2, yes. Of corollary 1, no.
Or it just says it follows.
Yeah, it just says it follows. Yeah, to me, it also was not clear that it follows. Is the microphone working? Okay, good. So, okay, that's fine. Okay, so let's go to this multi-qubit case.
You're not muted here. That's okay. So you should.
Yeah. Okay, so hopefully I will have time to cover this. So basically, the resolution to this problem is the following. We provide a counterexample. Of a non-stabilizer mixed state that is not distillable to a non-stabilizer single qubit state. So this is multi-qubit. Provide an example, non-stable mixed state multi-qubit that is not distillable. Not distillable.
Can I just comment on the first one? Could it be the case that twirling is the key thing?
The twirling is very key because it's a simplification. Yeah.
Maybe if you take something non-stabilizer, it maps you outside of the line that intersects the stabilizer.
So I thought of something along these lines, but you only are allowed stable Cliffords, right? So, okay. Yeah, no. Okay. So, say you have a state that, if you can also prepare such a resource state, uh, and you have a pure state. So what I'm trying to figure out is how the distilling. Say you were able to get a Hadamard state. How does that give you any H? You can, if you perform a Clifford, you will not get every.
But the twirling maps on the line, no matter where you start from.
Yes, but this. What is this statement? You have universal quantum computation whenever you have stabilizer operations plus some pure state.
Yes, I was saying maybe the pure state is mapped onto the line that intersects the stabilizer polytope.
Okay.
Smaller
Yeah,
line.
yeah.
You can only if it's a stabilizer state. If that's like the property of the twirling. Anyway, okay, maybe yeah.
A non-stabilizer single qubit state. So this is what we do. Okay, so okay, the strategy, I'll just say it verbally at first. What was the strategy with the single qubit case? You took the stabilizer polytope, and then you basically took a vector that crossed the boundary. That gave you a direction, and then you looked to distill something. You had a distillation algorithm based on this particular direction. You made sure that it was outside of the stabilizer polytope. So what we're going to do is consider, the 2-qubit stabilizer polytope. I'll just call it SP2. And what we're essentially going to do is look at a face of this stabilizer polytope. Just like we considered lines coming from H0 to H1, we will have something like an input state rho, which is directly from the face of the facet of the stabilizer polytope. And then we will consider a distillation where this is our input rho. This will be rho in, and it's a quantum state. Okay, so let's be a little bit more precise. Okay, so how does this 2-qubit stabilizer? So there's stabilizer groups that define stabilizer states. So I will not write all of them down, but there's a few. So you could have like I, x1, x2, xx, and you can do this for every combination of sigma 1, so sigma could be x, y, or z, and sigma 2, and there's 3 times 3, there's 9 such stabilizer groups. This is also not good. You could also have something like this. These are what we would call non-local polys. There's a poly on each qubit, and these all commute, and you can show that the product of these is equal to 1. So there's 3 of these. And then there's another kind, which will be like and for each of these, you can have, so the product of these is 1, product of these is 1, product of these is -1. And each of these polys can be plus or minus 1, so in the stabilizer group. So these are just the operators, but then we can give signs to them in various ways. It turns out that there are 60 2-qubit stabilizer groups of size where the size of them is equal to 2 to the n. Yes. So these define a stabilizer state. There are, of course, and then there's like I and XX and whatever. And in general, for 2 qubits, well, in general, you have 4 to the n polys for n qubits. Stabilizer, well, for each stabilizer, yes, because the group, well, 15 times 4. Yes, so you wouldn't consider those to be different groups?
Groups are 15, and then you have different value signs. So I think stabilizer state.
Okay, we can do that. Okay. And so here we have 4 squared polys. For the purposes of time, I do want to just say, I don't want to go through all of these, but there's 4 to the n polys. So we can write any density matrix in terms of these polys. The poly operators form a basis, but the thing is, we want density matrices to be trace 1. So it will be the case that we can write any density matrix in terms of 4 to the n minus 1 polys. So maybe I write any density can to the n minus 1 polys. So no coefficient on the identity is what I mean there. Or the coefficient is fixed, rather. Okay. So, so how do we form this stabilizer polytope? Well, we have 60, just like we did for the single qubit case. You had, in that case, 6 stabilizer states, and you took the convex hull. So we will, so just for completeness, let P, S, and the plus or minus signs can be written as some gamma be a or I just say a stabilizer state corresponding to one of these stabilizer groups in a particular signing. So then the stabilizer polytope, and I mean supposedly this, I only wrote it for 2, so is going to be the convex hull of these pi minus gammas. So there's 60 of these. They can all be written in terms of polys, so we can embed this into a real vector space of dimension 4 to the n minus 1. For 2 qubits, that's 15-dimensional space. So let's see, let's give some data about this polytope. So one number of vertices is just the number of stabilizer states equals 60. And then there's a dual problem of, so if you have the vertices, you might want to find the faces of this polytope. So the number of facets equals 22,320. And these fall into 8 orbits under CL2. So just to clarify, because we didn't go over much polytope theory, if you have a polytope like this, for example, there's the symmetries of this polytope are ones in which you can permute the vertices into one another and keep the polytope isomorphic. So, so if I permute these bottom vertices, that's a symmetry. But if I try to do, but this top vertex is different. So I can think of these as being colored in different ways. And so I have different orbits under the action of the symmetry group here, which is just the permuting of these 4 bottom ones. So this is one kind of polytope, and you can see that there's just different kinds of vertices in some sense because of the sort of combinatorial structure. For example, these vertices are incident on 3 facets, this one's incident on 4 facets. So you have different sort of vertices in a sense. So that's what I mean by falls into 8 orbits. Okay, so what we're going to do is we're going to look at each. So we will not look at each. We'll just give a representative example. But the basic idea is to take a face, one of the facets here, take one of the facets. We want a state that lies outside the facet because then it's non-stabilizer, but still a quantum state. So this will be our rho, and this will be a facet of SP2. And then starting from this rho, we will do a distillation process. Basically, what does that mean? It just means that we're going to project this rho. This will be our rho input, our 2-qubit state. And then we will perform a Pauli measurement, mapping it onto a 2-dimensional subspace, post-select on the +1 eigenvalue, and then see that the resulting state, when you decode it, will have always, except for one case. So for 7 facets, it's the case that this distillation gives us something that's inside of the stabilizer polytope. But for one case, it lies on the boundary, apparently.
you choose rho to be the facet?
Well, yeah. So you will choose it to have the same coordinates as the facet, and just, but it will have different coefficients than the facet.
So it will be rescaled towards the boundary, but not the pure state, right?
It's not a pure state. Not a pure state.
Facet either.
Yeah, not on the facet. It'll be somewhere between the boundary of the set of quantum states. It's not a pure state, and it's not a stabilizer state. Yes. So that's how he chooses the coefficients. So we have this rho. Y2 plus Z2 minus XX. Okay, and this violates precisely, well, at least it violates one inequality, which is the following. One quarter trace, or no, I don't think this quarter is necessary. Trace minus I plus Y2 plus Z2 minus XX plus. So this is one of the, so if I set this equal to 0, that would be a facet. This would lie on a facet of the stabilizer polytope, and anything that satisfies this in general will just be less than or equal to. Okay, so then we have this theorem that rho is not a mixture of stabilizers, but all 2-to-1 reductions output a single qubit state that single qubit stabilizer. When I say stabilizer state here, I just mean that it's in the convex hull of the single qubit stabilizers. It could be mixed. So here is the proof, and so it will not be a comprehensive proof, but what we'll do is we'll show it for a particular example. So, and then it's just redundant to show that it works for the rest of them. We can put it into a computer. So let SR be equal to right in our distillation algorithm, we have an input state, which will be this. It's a 2-qubit input state. And then we have to define a stabilizer state, which has dimension 2 to the n minus 1. So here, n is actually equal to 2. So, which in our case, n equals 2. This equals 2. That's what we have here. So it's still corresponding to what we did before. And then what we want to do is perform so we want to perform a projection. Let's call it just pi SR. So and we are post-selecting on the positive eigenvalue. So we have that this state afterwards, rho S, what we called before, is pi SR rho in, which is, I will just call it rho so that I don't have to change everything back there. Rho SR. And okay, so we will not normalize it for right now. And just, I'm going to show you at least, I'm not going to go through all the algebra. Let's do this 1/4. Okay, after some algebra, it's not hard. You can just use the properties, the algebraic properties of the polys, and you get that this is going to look like 1/8 I plus ZZ plus 1/3 Z2 minus XX plus XY plus Z1 plus YY plus YX. Okay, so now what we have is this state, and then what we want to do is we want to decode it. What does that mean? We want to move the logical qubit onto one of the physical qubits. The way to do this is by performing a C0 gate in this case. So applying it onto this state. Yes. So when you apply this, this is the decoding process. You get something like I minus 1/3 X plus Y plus Z tensored with, on the second qubit, 1/2 Y plus Z on the second qubit. And then, so this is our reduced state that we have here. Do I want to get rid of this? Let's try and fit something in here. Yes. So what is the state on this? The state on the first qubit is the state that we want to extract from the distillation. So I'll call it the reduced state. It's not normalized. So after you normalize it, or sorry, we will just keep it like this. It's not normalized. I minus 1/3. It's just this X plus Y plus Z. And if you just note for a second, we said in the beginning of talk how to determine whether something was inside of the stabilizer polytope or not. You sum the absolute values of its X, Y, and Z coefficients. Equals to 1. So it's lying right on the face of the stabilizer polytope. So it's a convex mixture of stabilizers. Okay, so you don't, even though you started with something that was a mixed state that was not a stabilizer mixed state, you, after this reduction, you still get something that's a stabilizer, or in the convex hull of the stabilizers. Yeah, this is just one reduction. This was one choice of poly, and then you could do it for others. But then also you can, through a computer calculation, you don't do it all. you could do this exact same thing. Pick a face, and then pick a state that violates it, and then do the same, and then do that for every single poly. I mean, there's too many. I'm not.
Okay, so they check.
Yeah, yeah. I will not check it by hand, but yeah. Yes. So exactly. So and then this part you can sort of see what it looks like, and then you can check by hand after that point, or sorry, by the computer. Okay. So let's just say a couple of things, and then we can wrap up. Yes, so this is one of the comments I was going to make. This is basically giving you the basic template for how the algebra grows, but then you can just apply this more or less and see how that functions. There is one remark. There is a particular inequality face for which this one gives an answer that's, if I'm not mistaken, this is also on the boundary. So, but Reichardt singles out this particular inequality. This doesn't, I don't need this. Singles out this one as being, having some slightly different properties. Minus Z2. Yes, so this one, when you do this 2-to-1 reduction, it's the reduced state of the single qubit. This one is also looks to me like it's on the boundary, but there is something special. So in our notation for Cihan in the audience, this is lambda type 2.1. And it has the property that it may be distillable.
The previous one was type 1, right?
Yes. But they do it for all of them, is what they claim. Yeah, he checks in the, yeah, all 8 types.
And this one, except this one, all of them are mapping into the stabilizer.
Yes.
But this one is not.
This one is lying on the boundary, and he says that there's a possibility that it could be distillable.
Boundary of what?
The boundary of the stabilizers, of the single qubit stabilizer polytope. The reduced state, the analog of this, is on the.
That means it's inside the polytope.
Yes, but yeah, I also was not sure why he thought that that was a good thing. He said it was on the boundary, but he said also that the limits of distillation in that particular direction. So.
Oh, you can rescale this slightly more with the boundary.
Yeah, so it's somewhere on this boundary, but you know, these distillation algorithms sort of specify a particular direction. For example, this H state, we specified this direction, right? Yeah, so these distillation algorithms, you might not know what the thresholds are in various directions. Yeah, so that's something to keep in mind. There's a result by Campbell and Brown also that says that, I believe it's for qubits, if I'm not mistaken, that there's always these bound magic states, right? Like, what does that mean? It means that they're outside of the stabilizer polytope, but can't be distilled. So I guess this is an example of that. Okay. Let's see. Any questions? Okay. So that's it. So next week we will see what's going on. Okay. Yes. Yeah.